Alright, it's down in the Zorro, and we're going to show you guys how to use a modified Atwood machine to basically get acceleration data as we vary the pulling force on a cart. Modified Atwood machine consists of several parts. There's a cart that's free to travel on a surface. It's being held back by this textbook right now. There's a rope that's looped over a pulley, and there's a hanging weight. And when we pull the cart back and take the textbook out, we expect the weight to fall and pull the cart to the side. It turns out that this is actually a really good way for us to get a quantitative test of Newton's second law. We know that we expect that having more mass means less acceleration. Having more force means more acceleration. And we tested that in class with the scooters in the hallway. But in this video, we want to get some quantitative usable data to see if this pattern is really true. Just like in class, there's a couple of things we can test. We can vary the force and check how that affects acceleration. If we do that, we have to keep the mass constant. And we'll show you how we do that with our modified Atwood's machine. Later, we will vary the mass while keeping the force constant. So to do these two experiments, what we need are force and acceleration data, and we expect those to make a linear graph when we graph them, and mass and acceleration data. We expect a hyperbola or inverse graph when we graph them. What makes this a little bit challenging is that getting acceleration data is not simple. It's not trivial. There's a couple ways we could do it. We could measure the distance a cart goes and time it, but that would be basing all our data on one data point. We could hook a ticker tape timer up to the cart and measure dot distances and figure out velocities from that and accelerations from that, but that seems like a lot of work. One thing we've got going for us is that for constant acceleration data, the velocity time graph should be linear, and the slope of it should be the acceleration. So if we could find a way to collect velocity and time data and make that graph, we should be able to get the acceleration pretty easily. It turns out that a pulley called a smart pulley actually can get us the data of how fast the whole system is moving as time passes. Let me show you how a smart pulley works. This pulley is what's called a smart pulley. And I'm sure you can see that there's a purple light on one of the plastic horns here. And this is called a photo gate. Right now, that purple light is visible on the other edge by a sensor. But when I pull the cart back, it gets blocked and unblocked as these holes move in and out of the way. So how quickly that happens, that actually lets the computer know how fast the cart is going. Interestingly enough, you can see that purple light, but I can't. It's not really purple. It's a color called infrared that our eyes can't see, but our cell phone cameras are sensitive to it. And for some reason, they display it as purple. What we're going to do is we're going to pull back the cart, and as it's being pulled by the hanging weight towards the edge of the table, that will be giving us the acceleration that we need to measure. So right now we got a 100-gram weight hanging off it, and I'm going to say go. And what I'm going to do is I'm going to fit a curve fit for the velocity time graph. I'm going to tell it to use a linear fit and to try the fit. And I saw a slope of 0.1237. So I'll go over to my spreadsheet program and I'll add that in for my acceleration for 100 grams. 0.1237. Mr. Nazzaro is going to take the 100-gram weight off. He's going to put it on the cart, and now he's going to take a 200-gram weight because we need to keep the mass of the system constant, or else we would be changing two variables at once. We have to clear all our data. Go. And we'll just keep doing this until we've got all the data. So we have position, velocity, and acceleration versus time graphs. And in theory, we could get the data from any of them. But the easiest one to get it from is going to be the velocity versus time graph, because the slope of that graph will be the acceleration. The acceleration versus time graph would be easy, except Logger Pro kind of calculates it wonky. Notice our velocity time graph is somewhat complicated. It includes the part where the cart hit its barrier. So we're going to want to just select the part that represents when the weight was pulling it, which is this nice straight line. Here's our curve fit. We can see the slope is 0.5549, which we'll put in our spreadsheet. So this is from another time we've done the experiment. And it's not strictly necessary to see, but what we've done is we've put all of the velocity time graphs we used to get the accelerations into the same graphing window. And you can really see that the largest pulling force gave the steepest velocity time graph. The least pulling force gave the shallowest velocity time graph. This isn't what we need to do to show the relationship between force and acceleration, though. We're simply going to take all of these slopes and put them into a spreadsheet and plot that versus force. So here's our data in the spreadsheet. All of the slopes of those velocity time graphs we got, they're all plotted here, along with the hanging mass. We've converted that into a weight or a force in newtons by multiplying each mass by 9.8 in column D. So we can see our graph of force versus acceleration indeed is linear, and it has a slope of 0.2387. Let's think about what that slope means. If we take our net force equation and write it like this, and we separate sigma f and m away from each other, we can sort of guess what that slope must be. Lining this equation up next to y equals mx plus b, which I'm doing because I'm putting force on my x-axis and acceleration on my y-axis, tells me if I do that, the slope of a linear graph I might get, linear because y equals mx plus b, signifies the inverse mass. The total mass of the cart was 4.01 kilograms. 0.2387 inverted is about 4.2 kilograms. So it seems like this is a really elegant test of our Newton's second law model. We do have a linear force versus acceleration graph, and we have a slope that seems to signify a property of the system, the total mass that we kept. We've gotten all our data on force versus acceleration when we were holding our mass constant. At this point, we're going to hold our force constant. We've got down here our 200 gram hanging weight, and we're going to basically put all of these weights on sequentially, so we'll have different masses being pulled with the same force. So here's our data for mass versus acceleration. As you can see, it kind of looks like an inverse graph. But unfortunately, spreadsheets are not great at calculating the inverse function. So we have to use a little trick to figure out how to get quantitative data from this. If we start with our Newton's second law, sigma f over m equals acceleration, line it up again next to y equals mx plus b. But instead of putting sigma f on the x-axis, we put the inverse of mass on the x-axis and acceleration on the y. That suggests I should get a line, y equals mx plus b, and the slope of that line should be the net force. So how did we do? We put the formula equals 1 over a2 into column D, row 2, got all the inverse masses. And when we plotted inverse mass versus acceleration, we did indeed get a line, as we predicted. And the slope of that ended up being 1.29. Now, we had a 200 gram mass, and that's 0.2 kilograms. So if we multiply that by the acceleration of gravity, 9.8, we see that the expected net force was 1.96 newtons. So we're in the ballpark, but not exactly what we would have predicted. Given that our data, though, does appear inverse here and very linear when we inverse the mass, I think we're looking at some sort of systemic error. And our best guess is that that's probably friction. So we hope you enjoyed this look at how you check Newton's second law quantitatively. Just to summarize, we calculated high quality acceleration versus force data, acceleration versus mass data. It fit our models of linear force versus acceleration, inverse mass versus acceleration, and the slopes of them had a fundamental meaning to our system, and the slopes of those graphs ended up close to prediction. So this seems to be a very good test of Newton's second law.